All right, if you were to go into Schoology, there is, in the projectiles folder, on the very bottom, this PDF that is range with time and angle. So if you go back to the problems that we did, like again, where someone's kicking a football or kicking a soccer ball, there were two things that we had to know in order to calculate our range, our maximum height, our hang time. We had to know the velocity with which you kicked it, right? And we had to know the angle that you kicked it at. The question that I'm raising to you is, can we find range, can we find x, only knowing the angle and the time that the projectile is in the air? So this goes back to, I'll tell you where this kind of piece of our unit came from was when I did the potato launchers for physics class. We did this for a number of years. And we went down to Southwestern University for their brain games one year. And this was an activity they did, was you had to build this little quick potato cannon or launcher in some way, and you had to actually shoot it and then guess how far it went based on the math. Does that make sense? So this would be the same kind of thing. If we were to launch your rocket, right, and we actually launched it at a bit of an angle, now we're going to launch it straight up, and so any kind of movement in the x direction is going to be just because of wind. Is that you with me? Theoretically, it should go straight up, come straight back down. But if we were to put it at an angle, we could actually, you do the math and figure out how far away it would go based simply upon how long it was in the air and what angle we launched it. And what I do want to do is I want to show you how we derive that formula. Again, I will put this is already up on Schoology. I don't expect you to memorize how to do this. I just want you to see it so you understand how we got what we got. Does that make sense? So we're starting with two equations that you should know very comfortably by now. Then if I want to find the range, right, the distance is just velocity times time, right? But notice that I had to take the initial velocity and get the cosine of it. If you remember, right, if I have velocity, and VO is just meaning your initial, right, the starting velocity, right? Then I got to break it into pieces, right? That here is my x, my vy, and here's my vx, right? In order to, if I know this angle, if I want to find this x, I'm going to use cosine. Here, I'm going to use sine. So they're just simply putting that into the formula. Does that make sense? Come on in, Joyce. Are you with me? Maybe, theoretically. If I want to find the y height, again, going back to that same equation that we used in the past, this would be the yf equals yi plus vit plus 1/2 at squared. Remember these equations? We've used them lots of times. We've changed the sign so that way we know that we can just put in 9.8 here and we know that it's going downward, right? And we changed a to g because again we're using gravitational acceleration. So let's do the math so you can see how this goes. Again, we want to find x knowing only the angle and the time, and we want to get rid of velocity. In other words, determining how fast something goes as it leaves is not an easy thing. We've tried this a number of times with our rocket launchers or our potato cannons, and it's not easy. There are ways you can do it, but it's not easy to do. So what if we just get rid of that totally? Can we find out how far it goes? So, if we say that the y distance is 0, in other words, it goes up, it comes down, and the height doesn't change. Does that make sense? It lands at the same height it's launched from, is basically what we're saying here. Then we can put a 0 in here, right? We cool? And I want to get this solved for VO, because remember, I want to get rid of VO. I want to take VO and get it out of this equation by plugging other things in for it. So by doing this, I can move this guy on the other side and then get rid of the sine and the time. And I I end up with an equation that looks like this. That VO is equal to x distance divided by the cosine of theta times t. Sir. And again, this is all right there on Schoology, but yes, I don't mind at all. It is there for you. We're taking the y equation. We plugged in 0 for y, and then we're switching the equation around to get VO all by itself. All right. So, what I'm going to do here then, and by the way, so we did this for our, this is our y equation. This was our x equation that we solved for VO, right? So now we're going to take that VO and we're going to substitute it into this y equation, right? So where this VO is, let's pop in our solved out x over cosine theta times t. So I guess it looks like this. And let's do some simplification here, that we can have x multiplied by these two divided by cosine theta. Right? Our t's canceled out because there's one on top, one on bottom. So gt squared divided by 2 equals x sine theta divided by cosine theta. I want to get x by itself because, again, I want range. That's the point I'm trying to find here, is to solve for range. And I get this equation, that x is equal to the cosine of theta times gravity times time squared divided by sine theta times 2. So this is a way that I can take these equations and derive from them the range, knowing only what planet I'm on, the gravity, how much time it was in the air, and what angle it was launched at, the velocity of its angle. The angle of its velocity, excuse me. Are you with me, my friends? Again, I would give you the equation. I'm not necessarily, you don't have to memorize per se, but this is what we want to use this for. Yes, sir?
Something going that gets launched faster when you throw a photo, something gets launched like not as fast. Like a bullet with less grains of gunpowder, it won't go as far as a bullet with more grains of gunpowder. So like, how do you find it with that? Because if you don't know how fast it's going, like, what that change do?
What it's basically, and I agree with you completely. What it's basically saying is, how much time is gravity affecting this guy? That's really what it's doing. And no matter what angle you're putting it at, knowing those angles and the amount of time it's in the air, you will find that. Because you're right. You are correct. The distance, because remember, y and x are independent, right? So gravity is still going to work on it at the same amount of time, no matter what, no matter how fast it's going, whether it's a bullet or whether it's just somebody tossing it nice and slow. The red equation is just saying that if the height is different, so let's say you launched it from up on a hill and you've got distance that it travels downward after it reaches the same height, then you just need to add that into your equation on the top here by adding that y distance, because now it's traveled some distance downward in the y direction. Shall we try one of these so you can see it in action?
This is all just trying to find the range.
All of this is just finding range. It's not doing anything else with any of the other pieces. It's just simply finding range. So, let's give it a shot here. Put those on the back burner for a second. Again, my equation is x equals cosine of theta. What else? Gt squared all over the sine of theta times 2. Okay? This is how I find my range. Okay? So, let's say that Matt is kicking the football, kicking the soccer ball, right? And he kicks it at an angle of 62.5 degrees. And the time it stays in the air is 5.23 seconds. Are you with me? Let's plug him in. See if we can't solve this guy out. The range is equal to the cosine of 62.5 times, what's my g? 9.8. And I can just use it as a positive. It doesn't have to be negative because I already took that account, the negative sign, into account when I, when I did my math. Again, the very first piece of my equation up here already had the negative sign in it. So we already took that into a consideration. Wanted to make sure you saw that. Okay, times 9.8. And then my time squared, 5.23 squared, divided by the sine of 62.5 degrees times 2. Talk me through order of operations here, because that's always where it seems folks get messed up. What do I want to do first with this? I want to square it, right? And then multiply the tops, then multiply the bottoms, then divide. Again, if you can put it in with the right parentheses, everything into your calculator, that's great. But I want to make sure you knew that you have to follow that order, and your calculator will do that if you plug it in right to get the correct answer. So what do we get? 69.7712. Okay, how would you round that? 69.8. What's my units? Meters. Because I'm range, right? I'm distance that we're traveling. Not that I don't trust Tanner, but that was what you all got? 69.8? Anybody else plug that in? It sounds right to me. That's a long time to be up in the air, so I expect it to go a good long distance. But Matt's a powerful kicker, so I'm not surprised. Does that make sense? The key piece, the piece that I want you to know from this, the reason why we're doing this, is because I want you to see that you can take these equations that we learned and use them in many, many different ways. Again, those of you who are taking calculus, you know that you can take and you can, all of these equations are related. Does that make sense? They all go back to the derivative of how these pieces work. You can find them without significant difficulty if you understand how to do these things. That's my point, is that we can take and move these things around and find new things just depending on what we're given. Okay, so what I want you to do is I've got 3 problems here. They are up on Schoology as well. I want you to try it. Use the equation, pop these guys in. Okay, again, this will be due tomorrow. The appreciations I've put on for Thursday. Thursday? It says on here, yes, Thursday. As long as you have them done by Thursday, I'll give you the 5 points for them. Okay? And again, you got 10 minutes. Rock and roll.